Let's get started. So I've been your session chair and now I'm a panelist, so I will moderate myself. I'm Chiara Mingarelli, this is Steve Taylor,
Hello.
Luke Kelley, and we're going to talk to you about supermassive black hole binary populations. So just as a primer, or maybe we'll just say as a roadmap, we're going to look first at the gravitational wave background and have a discussion with you, and then move on to individual sources, and then have a discussion with you again. The word of the day is discussion. We were told very clearly that things should be discussions, and we took that really seriously. So we want to, first of all, remind you of the scaling relations for the signal to noise ratio of both the gravitational wave background and individual sources. So for the gravitational wave background, the SNR goes like the number of pulsars and the square root of time. Cadence is not so important for the gravitational wave background. So that's every time you go back and look at your pulsar and time your pulsar. This is really one of the big motivating reasons that Nanograv is not working by itself, but with our European and Australian partners, and recently India with GMRT joined the International Pulsar Timing Array. So we have both more pulsars and longer time spans for pulsars that we share. So the EPTA and Nanograv share a lot of pulsars because they're all in the Northern Hemisphere, but there's not so many that we can time in the Southern Hemisphere together with the Australians. So we want more pulsars all the time and longer time spans. So with the individual supermassive black hole binary systems, we call these continuous gravitational wave sources. Exchangeably, we'll probably all say both of them at the same time. This goes like the square root of the number of pulsars, the square root of the time. Importantly, it goes like mass to the 5/3. So here, cadence becomes really important. You have to go back and time your pulsars really regularly, and you want to have really, really good arrival times or residuals for those pulsars. So one of the things that we get asked a lot is what happens to your detectability of individual supermassive black hole binaries in the presence of a gravitational wave background, right? You may have heard about the latest Arzoumanian et al. Paper where Nanograv and, well, now both PPTA and EPTA have all detected a common red noise process, which could potentially be the amplitude of the gravitational wave background. We'll find out sooner or later if that's true or not. But how does that interfere with our ability to detect individual binaries? So this is a figure from the paper that Chung Shin led with myself and Jeff Hasboon. And what you see here is gravitational wave frequency and the strain. And so these darker lines are the original IPTA pulsars that we have right now. And what we're doing is that we're extrapolating into the future. And we're saying, well, what happens to our total aggregate data set if we start with our IPTA data set and we turn on SKA1? We have SKA mid and low. We start to find new pulsars. And those pulsars only have short data spans. So those data spans are 3 years. You can see how these lines come in. They're sensitive right around here. And then their bucket is in a totally different place than the IPTA pulsars. What happens is that this really flattens our sensitivity curve at low frequencies, which is really great for detection prospects. Now, this is in the absence of a gravitational wave background. If you do have a gravitational wave background, that affects things at very low frequencies. So if your supermassive black hole binaries have frequencies of around 1 nanohertz, it's really important to have a good way of subtracting the gravitational wave background signal. But if they're at higher frequencies, which is the case of things that might be in CRTS or PTF or other surveys, then it actually doesn't make, that's going to be a problem. It doesn't make such a difference. Does anyone have a charger? I can. Great. That's all I had to say about that anyway. There we go.
Okay, so taking a step back for a moment, I'm super glad that we talked a lot about red noise in the previous discussion session, because one person's noise is another person's signal. And essentially what we're looking for is the primary target signal in pulsar timing arrays, thanks Chiara, is the accumulation of gravitational wave signals from every binary system out there, making a stochastic gravitational wave signal that looks like red noise in pulsars, except this red noise is correlated between pulsars on the sky in a very distinctive way that we can't think of anything else that you predict as correlation signature. So we leverage that as a template. What you're seeing here on the y-axis is the characteristic strain amplitude of a gravitational wave background that's referenced to a frequency of 1 over a year. So that's about 32 nanohertz. And then along the x-axis here is time with, this is when I wrote the paper, and then this is where we are now. And on these, on this plot is showing detection probability as a function of time. And these different lines here correspond to different degrees of detection probability. So what Chiara has done here is contrasted different theories of the gravitational wave background and when we might be able to at least constrain or, rule out some of those assumptions. On the floor here, the minimum level of the background that we might expect is from Bonetti et al. 2018. This is where you have severe overestimation of black hole masses. You can't get them to merge together through other mechanisms, so you rely on scattering from other black holes. Even this kind of mechanism, that's the worst case scenario, is something that we would detect eventually. That does still give you a gravitational wave background. Now, the best case scenario is when nature really likes us. This is the McWilliams et al. Model. We have no problems merging the black holes together. Black hole masses are not overestimated. And then just to contrast what Chiara mentioned, the nanograv collaboration and the European Pulsar Timing Array and Parkes Pulsar Timing Array have all seen what we call a common red noise process. Now that means something that has the similar spectral properties across many of our pulsars, but we don't have that set of distinctive correlations that we would otherwise use to declare a detection of gravitational waves. So we don't have that yet. However, things change very quickly. The situation is very fluid. Once you get a common red process, you might expect correlations to arrive quickly. So the answer to this question of whether we're seeing something as a gravitational wave background or not will come very quickly, we expect, within the next year or two. So we should have answers one way or the other very soon. Anything else anyone else wanted to mention about this slide?
Kudos to Alberto for having the closest point to the current estimate.
Yes and no. Yes and no. Alberto knows that those are all of the models.
I have points everywhere because I know what the uncertainties are. Sorry.
Next.
Yeah, so I'll try to go through this a little bit quickly so we can get to the discussion portion. But what I really want to try to convey here is that the gravitational wave background, it's not just a one and done detection. It really encodes detailed information about the massive black hole binary population and also their evolution. So I think the best way to see this is actually looking at how we calculate the gravitational wave spectrum in practice. And this is really the integral over all sources in the universe. This was really developed by Sterl Finney a couple of decades ago. But what's important here is that it has terms both for the population. Here I'm writing that in terms of the number density of binaries in bins of mass, redshift, mass ratio, frequency. And then there's also this evolution term, which here I've written as the frequency divided by the change in frequency over time. So this is a characteristic time scale at each frequency. And the way of seeing why this is important is you imagine that these black hole binaries are starting at low frequencies, and as they in-spiral, they move to higher frequencies. Now, the faster they move, the less time they have to emit gravitational waves, so the less gravitational wave energy is in that frequency bin. So that's encoded in the gravitational wave spectrum. And then, of course, you have the strain produced by each binary and then some redshift dependency. So if you plug in kind of simple analytic estimates for this, you get kind of a power law with a minus 2/3 spectral index, and that's showed with the dotted line here. But it's really the deviations from that encode interesting information. So the overall normalization of the gravitational wave background here mostly tells you about the number density of galaxy-galaxy mergers and also the overall mass distribution of black holes. So we can use that to kind of calibrate black hole galaxy scaling relations like MM sigma, MM bulge, etc. At low frequencies, what's important is the coupling to the galactic environment. So these are the environmental processes that we discussed this morning that mediate the in-spiral. So how effective stellar scattering is, the circumbinary disk torques, etc. That'll turn over the spectrum here because of that change in evolution rate. And then even at the highest frequencies, although this is the hardest to detect, this encodes some information about the eccentricity in the redshift distribution. So again, this isn't an individual one-time detection. This is really something that'll progress over time. As we increase signal to noise, we'll be able to measure more and more about the population of these systems.
Yeah, so thank you, Luke. I want to, before we switch slides, just bring your attention to the strong dependence of the characteristic strain on the chirp mass of the binary. Here it's not quite written out, but it goes like chirp mass to the 5/3.
Yeah, in the individual strain portion.
That's right. And so given that you can model the gravitational wave background that way, it also makes sense that a detection of a certain amplitude of the gravitational wave background should give you a handle on the number density of sources, the redshift that encloses the background, and the minimum black hole mass. And so my student, Andrew Casey Clyde, did exactly this. And so here you can see 1.9 times 10 to the minus 15 is this black line. This kind of looks really funny here. It took him a lot to convince me that this wasn't a bug in his code. So I made him make me a 3D image of like how this makes sense. And this is the strain, this is the characteristic strain intersecting with the plane here. So you can see, you know, this actually does make sense, but it took a while. So what we found is that the minimum mass that contributes to the gravitational wave background is about 10 to the 8 solar masses. And the number density of sources here is about 7 times 10 to the minus 6 supermassive black hole binaries per megaparsec cubed. And there's a rather large volume of the background extending out to about a redshift of 2.5. Now, the really interesting thing, in my opinion, is that this number density of sources is 5 times larger than the one that we previously expected in Mingarelli et al. 2017. So what does that mean? That there's probably a lot more supermassive black hole binaries that could be merging nearby. So this is only good news. So we have some big questions, and these are really questions for you all, right? Because we're here, we're all members of Nanograv, and you guys are all experts in gas-related things and black holes. So we want to understand something like this. Is supermassive black hole binary stalling consistent with what we've seen in pulsar timing array data so far in both PPTA, EPTA, and Nanograv? Does that even make sense to think about anymore? Sterile. We can go over some other questions if no one has any comments. Oh, Alberto.
I have a comment. Until the correlation is bulletproof and that's the gravitational wave signal, I would say yes. I mean, stalling is consistent because we don't know whether it's from a gravitational wave origin or not. And actually, if you talk to some cosmology,
no, I don't understand that at all.
What do you mean?
Well, because all of the models that have significant stalling have much lower amplitudes in the gravitational wave background.
Yeah, no, but exactly. But you have to assume that what you have now in the data is a gravitational wave background.
Is it consistent with the common red noise process is the question. We're not talking about that.
No, okay. Maybe not. Even if it's not, it doesn't have to be until that common red process is a gravitational wave signal.
But this is the question. We're confusing everybody.
Okay, sorry.
Well, I think another point
No. All I'm saying is that, right, stalling, according to our current models, doesn't appear to be consistent if this common red noise process really is the amplitude of the gravitational wave.
Okay, so a more maybe serious comment.
Yeah.
I would say, it's not 100% inconsistent in a sense that it makes everything harder because, as we have occasion to say already, also Zoltan mentioned before, right? When we allow stalling in our models and we wait for a third black hole to come in and make something, make a previously existing binary merging, maybe you lower the overall signal by 50% or perhaps a factor of 2, which makes that, you really need to boost the things like M-sigma relation, merger rates and stuff like that in order to produce that signal with stalling. Okay, so it makes it more difficult,
so this
but
is
not
Zoltan's
100%
paper.
impossible.
This is Zoltan's paper right here. right?
Yeah. But that's a
So
point
that was-
estimate, right? So if you take that model and you increase the masses of the black hole by a factor of 2, that I would say, why not?
Is that possible, or was that
might-
model already created with Cormindy and Ho as the MM bulge relation? Can you actually get more massive? Like, is that true?
I have no further comment. There are I think there are larger uncertainties in the Cormindy-Ho, in the high end especially.
Of course.
It's not really even a power law exactly.
But
So
now we have to get really fancy, is what you're saying. It gets more and more difficult. The more that you want to hold on to stalling as a real thing, the more you twist yourself into knots.
Sure.
And I think something else that Alberto hinted on, but didn't actually say, is that there could be a cosmological contribution to the signal that we're seeing, even if some portion of it or none of it is from supermassive black hole binaries, the favorite model. So there are alternative models from cosmological phase transitions, strings, primordial black holes, etc., that are maybe not quite as well developed.
Absolutely. Back here.
Thank you. Ian Chikala, Penn State. So can you go back to the slide that was
The color one?
Yes. So naive question. It seems like from a first detection, you will already have the ability to select from a number of different population scenarios. But moving from this slide to the next one that Luke presented, how much longer or how much more data do you need to really sort of drill down into these questions? Is it the kind of thing that happens like in a couple of years, or is it the kind of thing that's like order of magnitude needed to really sort of explore that differential?
Yeah, let me address that quickly. If we go back to the previous slide, these models are drawn as discrete stars, but really there's a huge amount they bleed into each other. Okay, so they're not easily discriminated against each other. We'll need very, very good amplitude uncertainty on the background in order to discriminate these, but it's difficult to tease apart exactly how they're different because there is huge spread between them. So like this, it makes it seem like they're delta function models. They're not. So that's a difficult problem to solve.
Just to add to that. Oh, sorry, Luke, was that you?
Yeah.
Go ahead.
Another way to answer that, there was a paper led by a postdoc now, Nihan Pol,
Yes.
who's now at Vanderbilt, who kind of modeled how we expect this signal to evolve over time. And based on that forecasting in the 15-year data set, which we're analyzing now, as Steve said, you can either confirm or refute whether this is a true gravitational wave background or not. And at the same time, you should get a roughly 40% accuracy measurement in the amplitude and the spectral index. So that'll already start to clean up this parameter space a little bit. But it's not until we get to something like the 20-year data set that you can really start to look at the shape of this gravitational wave spectrum. So in that work, for example, Nihan showed that you can start to detect the presence of a turnover at low frequencies, that type of deviation from a power law. So probably still something like 5 years or so to get that detailed information.
I have one more thing to add. So that's exactly right. We'll start measuring signals in all of these low frequency bins, right, one after the other. So this might look like a power law. It might look like it turns over. From the turnover, you might be able to say something about gas or eccentricity or stellar hardening. And also deviations from the f to the minus 2/3 power law could also be due to something else sourcing the gravitational wave background. So all nanohertz gravitational wave sources, whether they're primordial or astrophysical, will give you the characteristic spatial correlations that Steve was talking about, in this case called the Hellings and Downs curve. However, they'll all have a different spectral dependence. Right now, the problem is that they're all really close to -1, right? They're minus 2/3 for supermassive black holes, minus 7/8 and -1 for their sources. And so you have to really be able to have a lot of data. So as Nihan's paper estimates, about 20 years of data to be able to try to disentangle different sources of nanohertz gravitational waves. Yeah.
This is sort of a question that maybe it's bleeding a little bit too much into the physics or orbital evolution discussion, but this is something that came up in tomorrow's talk this morning, is this idea of the knob that is related to the mass ratio distribution and its concurrent evolution in these models. I'm wondering if anyone wants to comment on, to what extent is that a fundamental knob? To what extent do people feel like that's well understood? Because it seems like that, it really bleeds into like, okay, where is the stalling at what point? What frequency is it going to affect? I didn't get a good sense of that especially from the semi-elliptical models.
So in the models that I've looked at with my student Andrew Q, the mass ratio is not hugely important. It looks like the total mass is really important, but in fact the mass ratio of the binaries is the subdominant thing. Does anyone else want to comment?
Yeah, I would just add to that by saying that I have no information on the distribution of mass ratios, but the strain of the gravitational waves can scale almost linearly with that mass ratio. So if we do have a lot of low mass ratio systems and the distribution is skewed towards those, that can diminish our gravitational wave signal. Hopefully it doesn't seem to be that way.
Actually, we have a bonus slide from Magda that I think addresses this directly. Maybe I can skip ahead to that. Magda, do you mind saying a couple words here? Oh, if I can find that.
So Luke and I actually looked at how mass ratio evolution in the circumbinary disk phase affects the gravitational wave background. And so this is not shown in the slide here, but we found that can have a really significant effect on the amplitude measured. So in the most conservative picture, I think our boost in the gravitational wave signal was about 80%. And so we also found later on in different work that's just on the archive now, so please look at it, that eccentricity can also affect how much the mass ratio of the systems is boosted. And so the slide shown here, and this is a bit of a change in topic, but we're talking about populations, so I guess this is justified. You're seeing the preferential accretion rate as a function of mass ratio. And the blue curve and the fit is the preferential accretion for a circular binary that's accreting from a circumbinary disk. So now when we turn up the eccentricity to just a modest value of 0.2, we actually find that the preferential accretion is boosted. And so with mildly eccentric supermassive black hole binaries, you would expect that the gravitational wave background has a quite significantly higher amplitude as a result of circumbinary disk accretion. But now, if we do the same experiment with high eccentricity, we find that the preferential accretion rate is lowered. And so in fact, when we look at the timescales, there's almost an order of magnitude difference in the timescales at which low eccentricity binaries grow in mass ratio versus high eccentricity binaries. And so I think that, first of all, we have investigated the effect of that circumbinary disk accretion. And obviously, depending on torques, depending on how long the circumbinary disk phase is important, those estimates would change. But in general, circumbinary disk accretion can affect populations and the signal. But also, our knowledge about the eccentricity of the binary can then again modulate those populations. So biased view, I think it could be an important ingredient in estimating that.
Yeah, sorry for putting you on the spot there, but I think...
a quick clarification. The y-axis is accretion rate on secondary divided by accretion on primary, or?
Yeah, that's right. Yeah, so just the tie-in that I intended there is that you have kind of the initial distribution of mass ratios at the time of galaxy-galaxy mergers, and that's uncertain. How that is convolved with the coalescing fraction is increasingly uncertain. And then what Magda really showed is that during the evolution process, that mass ratio distribution can then be essentially fully scrambled and changed during in spiral. So I think there's tremendous uncertainty in this parameter.
And my models didn't have any gas. So that's a really interesting way of discriminating and just showing how important gas is in those systems.
I suspect we should move on to individual sources of gravitational waves since we've only got about...
Did you look at the time? That's crazy.
I know. We don't want to keep you away from drinks and dinner too much longer. But in addition to initially finding a gravitational wave background, we'll slowly start to be able to resolve individual sources out of that background. As Chiara mentioned earlier, And there are two roads that we get a multi-messenger detection of an individual binary. The first road is that PTAs find something, but it'll have very broad sky localization, maybe tens to hundreds of square degrees, okay? And within that volume, we'll be able to do some sort of host galaxy identification and then trigger a photometric follow-up and see if there's anything funky going on with the system. But that's a difficult problem, and we need some way of ranking the kinds of galaxies that would host a binary. This is something that Alberto and Jana Goldstein have worked on before. Many people have worked on the idea of what kind of galaxies would host such a system. The other possibility, the other road to a multi-messenger detection is that we've got lots and lots of these binary candidates from time domain surveys. Let's just follow up those candidates using PTA data and either invalidate them or hopefully find a detection, and then everything's great. And keep looking at that system. So two possibilities, and I suspect we'll get into those in the next slides.
So here we also have big questions for you. So what kind of galaxies host gravitational wave or electromagnetically detectable supermassive black hole binaries? That's a really big question because we know that they have to be massive enough to host these binaries. So maybe you're looking at massive ellipticals. It's not clear if there's jets. That would be awesome if they did, but what if they don't? Also, it's difficult because it can take up to, a few giga-years for it to go from a galaxy merger to a supermassive black hole binary merger. And so all of the morphological signatures could be gone by the time the supermassive black holes merge. Alberto looks like he has something to say.
Yeah. Well, I think it's probably safe to say that I will forget about morphological signatures because those things have giga-year timescale for going down the binaries, and massive galaxies experience a merger per several giga-years. So every massive galaxy would have had a merger within that time span, right? It's just one of them has a binary in the right phase.
Yep.
And so, I wouldn't count on morphological signatures at all.
We are in violent agreement.
So not on galactic scales, at least.
Sorry if I missed this explanation in the last slide, but could you say something about, PTA localization is not,
For all skies.
compared to single galaxies is huge. So what's the strategy here to identify a PTA single source with the EM source in that large error box?
So we can jump on to the next, be 2 slides time. Essentially, you need to work out some sort of ranking statistics to cut out some of those galaxies in this huge volume. So along the right-hand side here are the many people that have studied this in the past. Essentially, you want the most massive galaxies. Obviously, that cuts out a huge number of possibilities within that localization volume. And from Jana Goldstein's study in 2019, you start off with maybe hundreds of thousands of galaxies in a localization volume, and you can get it down to about 50 or 100, which is manageable to trigger some sort of photometric follow-up. What I wanted to point out here is some work that was led by Vanderbilt undergrad Katie Sella working with me and look. Essentially what Katie has done is to take all of the supermassive black hole binary systems in the Illustra simulation, track the galaxy properties with those supermassive black hole binaries, weight the binary detection probability in PTAs, and then find out what the associated host galaxy properties are. Okay, so this is trying to develop some sort of ranking statistic so that we can tackle this problem in the near future.
So yeah, this is, one way of, we can go this way. So we can go from having a large error box, then trying to figure out which galaxy it is. And then we can go the other way, like what we did in Shin, Mingarelli, and Hasbun, and look for things that we think might be supermassive black hole binaries and then follow them up that way. There's also some work that's been done looking for local supermassive black hole binary host galaxies. This paper came out in 2017, but what we found is that in our local 250 megaparsec volume, there should be something like 91 plus or minus 7 galaxies that host supermassive black hole binary systems, that very few of them might be stalled. And interestingly, the chirp mass that we most detected is 10 to the 9 solar masses. So that's interesting because you would have thought that perhaps galaxies that hosted more massive potential binaries would have been more detected. But it turns out that, you know, because the time to coalescence of the binary scales like the chirp mass to the -5/3, those ones would go through the PTA band too quickly to be detected in a particular realization of the universe. If the mass isn't big enough, then it's not massive enough to be detected. And so 10 to the 9 solar masses is really the sweet spot where it's both detectable, but your binary is not zooming too fast through the pulsar timing array band. And then what we did is to say over these 75,000 Monte Carlo realizations of the local universe, which galaxies most often hosted supermassive black hole binary systems. And we published this ranked list. NGC 4594 was the first one, many times. And this is the Sombrero Galaxy. And that was really interesting because the Sombrero Galaxy has a black hole, likely just one, but its mass is about 10 to the 9 solar masses. So if it were in a binary system, it would be incredibly interesting and would be basically the perfect candidate host galaxy for something nearby. And as Alberto and I were both stressing, this has nothing to do with morphological features. This is just based on the mass of the galaxy.
Hi, Chiara, this is Magda. I think this is really interesting work. I wonder if you also constrain the mass ratio distributions. I'm sure you do because you're giving chirp mass estimates, right?
Yeah, this, I don't think that I published that. This was in 2017, but I still have all the data. We could do that.
Great, thanks.
Do we have a last, oh, Magda slide. Let's go back to the questions because I think we still have 5 minutes because, yeah, that's what we have for now. Okay, Luke, do you want to walk us through some more of the questions that we have?
Sure. Yeah. So some of the other kind of stimulating questions that we wanted to address is how can orbital constraints from the existing binary AGN candidates that we have, how can that inform our techniques for doing gravitational wave searches? Any insights from the EM observations community or modeling? Or similarly, from that series of candidates, how can we go about distinguishing between the binary induced variability, true binary signatures, and then just kind of the intrinsic noise and variability in AGN?
I mean, that question in particular is, it ties us very strongly to the subject of this meeting and this program, because we need to be able to understand on what timescales we'd get electromagnetic variability. And if that's linked to the orbital period of the binary in some way, or the orbital phase of the binary, we can co-evolve a gravitational wave signal with that and model things together. So we'd like your input to understand that.
Scott.
Hi, I'm Scott Noble. So from our work of close binaries, we see that the lump modulates the accretion rate and thus the luminosity of even the mini disks. And so it's, for equal mass binaries, at least, it's pretty trivial to back out the orbital frequency from it if you know exactly that it's, you know, oscillating at this frequency, and that's the radiative mechanism. But you know, it's not the peak period of your luminosity of your light curve is not the orbital frequency of the binary. But that association diminishes probably. It gets more weighted towards the orbital frequency at smaller mass ratios, I would imagine. But
so Scott, are there any caveats to that? Does this work for any kind of system, or does it have to be circular? What happens if it's eccentric?
This is all right. Yeah. So these are all circular orbits.
all the angular momentum components are aligned. So yeah, there's certainly caveats there. Also, when we do a Fourier power spectrum analysis of the light curve, we do see red noise at higher frequencies, and then we see the peak mode on top of that red noise. So you still get the turbulence, right? That you would see maybe, I mean, who knows what a real AGN or binary AGN disk looks like, but if you're to assume that as a 3D turbulent disk, then you would just see these larger amplitude modes on top of the turbulent spectrum, I would think.
Just amplify.
Yeah, just a comment. This is Magda again. So the 5-orbit variation in the light curve that we expect for circular binaries, that just completely disappears once you actually look at even mildly eccentric binaries. So I would have the fear that this is a special case, and we can only see that variability in very few binaries. So I think we need to be prepared to model the variability for a much wider parameter space and look for maybe more interesting signatures that would occur in eccentric binaries.
So if they're emitting powerful gravitational waves, they probably are not eccentric, right? Because they've probably circularized due to gravitational wave emission. I'd conjecture. The eccentricity may be non-trivial, maybe, non-zero.
So they don't circularize so fast, right? So here we're still, so if you do consider the circular orbit and your equal mass 10 to the 9 solar mass binary is at 1 nanohertz, then you're 25 megayears from merger. So like we are in the in-spiral phase for a really long time, and eccentricity, of course, speeds that up, but you could still very possibly be quite eccentric once you start emitting gravitational waves, like detectable gravitational waves.
Okay.
I was just going to add the comment that if you are looking for a signal that's modulated by one of these effects of the streams crossing the gap, then you have to hope that you're observing in a band produced at the place where those streams strike the mini disks. Because otherwise, once the matter enters the mini disks, typically the inflow time to closer in, deeper into the potential is much longer than the timescale of the binary orbital period. And so that buffering in the disk erases the modulation.
So can anybody else add to that if we
Zoltan
expect?
Has a question, and I think that'll be our last question for the session.
Well, actually, the few things, but quickly, I just completely agree with Magda. For eccentric binaries, we also found the lump periodicity goes away. I think the other thing to make things even worse, I'm not sure the current searches, can you hear?
Yeah.
Yeah, the current searches, I think, might be biased for sinusoidal-like variability and may actually miss candidates which have non-sinusoidal flaring types of light curves. And the third thing, I think, I'm not sure I completely agree with Julian, because there are also shocks produced when the streams hit the mini disks, which can come out at higher photon energies, and you still get modulations.
Okay, that's awesome. We have one more question on Zoom, and then we're going to wrap it up.
Alex
And
Dittman.
we can continue our discussion over dinner.
Yeah, so I had a comment on the sort of 5-ish orbital period variability. So based on some of my work using locally thermal simulations at higher Mach numbers, as well as Westernacher, Snyder, and their simulations were ideal gas with cooling. But as you go to sort of thinner and thinner disks, both the accretion rate time series and the sort of luminosity time series become a lot noisier as you go to thinner and thinner disks. And I don't know if there's been much 3D work on these thinner disks, but sort of extrapolating to the sort of Mach numbers we expect AGN disks, it may just be swamped by noise potentially.
Hey, another interesting point. Thank you, Alex. All right, I think that brings this session to a close. Thank you, Luke. Thank you, Steve. Thank you, audience.
Thanks, everyone.
Yeah, wrap it up.